Ladies and gentlemen, boys and girls, children of all ages, it is now time for the greatest math lesson that you've ever heard in your entire life. We are going to learn about multiplying polynomials using a method that some of you may have heard of and some of you may have not. But it is called the Bechtel box. And as Mr. Bechtel, I am happy to be the one to describe this for you. Actually, legitimately, all I really did was take something that was in another math book at some point in time and share it. Some kid called it a Bechtel box, and I thought that was kind of funny, so that's kind of fun for me to talk about. Now, here is what we're talking about here. We talked about distribution before, and we've seen examples of distribution a whole bunch. And so, like, generally what distribution looks like when we're doing this is you'd have a number on the outside like a 5, and you have like an x plus 2 on the inside of parentheses, and distribution means you're multiplying everything from the outside times everything on the inside. So this 5 would go towards both. We would have 5x plus 5 times 2, which is 10. That's how we distribute. The problem is that there's sometimes that we're not just multiplying a single number times both terms on the inside here. We're multiplying another binomial, another 2-term set that's going to multiply with this 2-term set. And the thing about doing this in terms of a distribution is that since you're not just multiplying one thing, you have to have a way of distributing everything from here to everything from here. Now, the way that this works mathematically is it is just distribution. It's just that you're essentially showing where everything comes from. So I could take this 5x and I have to distribute it to both things. So I can show that I am multiplying that 5x times both things here. And then I can also say, well, wait a minute, I've also got to multiply that -2 times both things, and I can show that. So when I'm done with this, I'm going to have 4 different results that came from multiplying this. But essentially, you're just going through and multiplying them using the distributive property. So if I do this, I'm just going to kind of write my results here. So 5x times x, that would give you 5x to the second power. 5x times 7 is going to give you 35x, and it's positive because they're both positive terms. Then when I multiply this in here, and I've got -2 times x, I'm going to get -2x, and -2 times 7 is going to give you -14. Now, guys, when we're looking at this, you're looking at 4 different results, but essentially what you're doing is trying to find the like terms that you can combine. Generally, what tends to happen when we're doing this is you really only have one pair of like terms. They're normally those 2 middle terms because they pair a number with an x. So here, that 5x squared, we don't have any like terms, so that'll give us 5x squared. When I combine 35x and -2x, I'm going to get a positive 33x, and that -14 doesn't combine with anything, so that's going to give me a -14 here as my final result for multiplying this. Another thing that this has been called in the past is FOIL, F-O-I-L, and FOIL's fine. It's a mnemonic device used to remember which ones you pair with each other. This goes for first, outside, inside, and last. So when we think about it, our first terms multiply together, our outside terms multiply together, our inside terms multiply together, and our last terms multiply together. All it is a way of remembering to distribute twice. It doesn't matter how you remember it. The way that I tend to go and do this is the box method, not because it's anything mathematically different at all. In fact, it's exactly the same thing. It's just a way of organizing your numbers, and it keeps them separated in a way that allows us to see what's happening, and also it expands it so you don't have to use a 4-letter thing to be able to describe how to do this double distribution, because it's a little bit more versatile. And I'll show you what it basically means. What you essentially do when you're using the box method, or I could call this the Bechtel box, that'd be fine. The Bechtel box method, we take what we have here and we count how many terms there are in each of the sets of parentheses. Now in this case, there's 2 there. So we're going to be doing 2 by 2 here. So 2 by 2. So inside here, we are going to make a box that is 2 by 2. And what we're going to do then is we're going to use this to organize how we distribute each of these. Now, since both of them are multiplying times that x plus 7, I'm going to put the x plus 7 across the top here to kind of keep track of where these are going to be. Since each of these are what multiplies, I'm going to put a 5x here and a -2. So I can show the results when I do 5x times both. I can write them in these boxes. And -2 times both, I can write them in these boxes. It's just a way of keeping track of them. Literally, the math that you're doing is exactly the same is what we've done here. In fact, I'm going to use the same colors that we did before so that you can see where they came from. When I'm multiplying this, it's kind of like finding the area of this rectangle. If I do 5x, a length, times x as a width, here I get 5x squared. Well, hey, that's right over there. And then if I do this one, this is 5x is the length on this side, 7 is the length on this side. So if I multiply those, 5x times 7 gives me 35x. Exactly the same answer I got here. It's just organized in a different way. Now, if we're going to go through and do this the same way with that -2 times the x up there is -2x. And here that -2 times that 7 gives me -14. And then at the end of the day, what I can do is look at this, and it's kind of organized in a way where we can find our like terms, because nearly almost always they're going to be sitting here on the diagonal for us to kind of look at and see what we can have. So when I'm done, I will still have 5x squared is something that doesn't have a like term. These two combine to a positive 33x. I've got that -14. It's literally the exact same answer. It's just giving it to you in a way that we can organize our results and show where everything came from. Now, I don't care which method you use. Clearly, I prefer the one that's named after myself because I have too big of an ego and I would like to speak of my name as often as I can. But the bottom line with this is they're both different ways of organizing it. This method is more versatile when you have different types of problems, but a lot of our work is going to be just 2 by 2. So whether you're doing distribution or FOIL, or you're doing the box, the Bechtel box method, they're fine. I'm going to show you this next one the same way with both. And then we're going to show you kind of why the box might be a little bit more useful when you're going to be using it for different types of problems. So we're looking at this one right here. Here we're doing the distributive property or foiling. All right, fair enough. I'm going to rewrite the problem in both cases so we can kind of see it. So we have 3x plus 2 times 2x plus 5 right there. And then I'm going to write those on the outside of this box here. 3x plus 2 and then 2x plus 5. Okay, so we've got the same work. We're going to be doing the same thing. It's just another example of both. So real quick, let's bust this one out here. Bust out a Bechtel box on this bad boy. So here we go. We're going to do this one with just foiling. So 3x times 2x is 6x squared. 3x times 5 is 15x. And if I do these ones here, 2x times 2x is 4x. 2x times 5 is 10. When we look to combine like terms, those are our two like terms. 15x plus 4x is 19x. And we just bring the other ones down because, as we know, we have to know where everything came from. When we're doing this in math, did a pretty good job there. I'm going to do the same work over here. I just want to show how it fits into the box. This one is 3x times 2x or 6x squared. This is 3x times 5 or 15x. 2x times 2 is 4x. 2 times 5 is 10. Combine this diagonal, and we get the same answer, 6x squared plus 19x plus 10. Now, I know it's not exciting, and really, it doesn't matter if it's exciting or not. It is just a different way of looking at it and showing you these examples in two different ways. Anytime you're multiplying polynomials, which is basically groups of monomials together with pluses and minuses, you've got to find a way to distribute more than one thing at the same time. It's not just a single distributive property. It's going to be double or triple or quadruple distributive property. And that's why the box becomes a little bit more useful. Okay, so if I'm looking at this, give me just a second. I'm sorry about that. Too many things happening. What you're going to have to do is you're going to have to look at what we have here and say, if I have something like this, we've got two terms, and then I got a three-term set, I can't really do that FOIL thing because there's firsts are these, outsides are these, insides are these, lasts are these. I missed that 5x completely. I really prefer doing this in a box method because I can just continue to create this graphic organizer and see where everything is at. This is two terms, so it's 2 by 3 terms, 3. That means when I make this box, it's got to look like this, where I've got space for everything, okay? That 2 side there, these have to go on the side, so I'll have a 4x and a plus 3. Here I've got these three terms, 2x squared minus 5x minus 3. And so now I've got a place to put all of my answers. Now I'm going to get 6 of them. And if you did want to distribute it by taking that 4x to all of them and 3 to all of them, it would be the same. But as you start to expand the number of terms in your polynomials, the longer and longer and longer this tends to get because you have to keep track of where they all are. You have to find all of your like terms. As I said before, if these are organized well enough, Most of the time, your like terms will sit on the diagonal. So this is a pretty good way for us to organize it. Now, that being said, we're going to do some multiplication. You do need to look at your laws of exponents a bit here, because when I'm multiplying a 4x times a 2x squared, I have to remember x to the first times x to the second is going to be x to the third power as my exponent there, and the 4 times 2 is going to give me 8. Now, I think you'll be okay with the rest of them, but just don't forget that you do have to continue to use that 1 as you expand these. So 4x times negative 5x is negative 20x squared. 4x times negative 3 is negative 12x. Numbers are starting to get bigger, which I think is kind of cool. 3 times 2x squared gives me 6x squared, and if you notice, its like term is diagonal there. 3 times negative 5x is negative 15x, same thing. And positive 3 times negative 3 will give you a negative 9 here. So as we look at those diagonals and see, well, there's a set of like terms, there's a set of like terms, it gives us a way to combine our things and know what we're going to be doing. So as we do this, 8x to the third power is our first term because it doesn't combine with anything. 6x squared minus 20x squared will give me a negative 14x squared. Negative 15x and negative 12x is negative 27x. And at the end of it, I've got that negative 9, which combines with nothing. So I have a 4-term polynomial at the end of this by multiplying a binomial and a trinomial. Now, really, everything that we're going to be doing is some expansion of this, but I really like this next question. And when we talk about this next one here, we're talking about multiplying 3 binomials together. And it has here as a hint, think about how you multiply 2 times 5 times 3. And it's a really good question because as we look at what's happening here, there isn't anybody that can take 2, 5, and 3 and just pop, there's an answer in their head. Because when we do multiplication, multiplication is an operation that functions in sets of 2. You multiply 2 numbers together, you get a result. Then you can multiply that result times 2 other numbers. So if I'm looking at this, the order that you multiply this in doesn't matter. But I can't just say, well, of course, 2 times 5 times 3 is 175. How do you not know that? I can know what each of the pairs are, and that's kind of what I want us to do. So if I take 2 times 5 to get a 10, then I multiply that by 3, that's going to give me 30. We're in good shape. Or if I want to do 2 times 3 first and get a 6 and multiply that times 5, I'm going to get the same 30 there. The order of that doesn't matter, but what does matter is you have to multiply these one pair of things at a time. That's the same thing as what you'll have to do if you multiply 3 binomials together. You pick 2, multiply them together to get an answer, and then multiply that result by the third one. And it's not too hard to do, it's just something we need to pay attention to. So let's say I take those 2 first. That x minus 7 is going to stay put until we're done with it all. So if I'm doing this, that's going to give me here, I'll put x minus 2 on the side, I'm going to put x plus 4 here on the top, and I'm going to multiply this in the Bechtel box to see what we're going to get. So we'll have x to the second power, 4x, negative 2x, and negative 8. So if I combine all of what we have right there, my new polynomial is now going to be a trinomial because these diagonals combine, and I'm going to get x squared plus 2x minus 8 as my result. Now I'm going to bring this guy down here for our next multiplication, because now I can multiply this result times x minus 7. It was just like taking 10 times 3 or that 6 we got times 5. You take the result of the first pair, you multiply it times that last factor that we have in there. So the difference between the way this works and the last one is, well, here I've got a 3-term by a 2-term. So if I'm going to make this, I'll try to do this in a way that's not going to be too out of bounds for the amount of space we're taking up. 3 by 2 looks a little bit more like this. So if I do x squared 2x or plus 2x and minus 8 on this side, and I do x minus 7 here, the organization is going to look a little bit different, but at the end of it, you're still going to have the same kind of work that we had. So here, x squared times x is x to the third. Negative 7 times x squared is negative 7x squared. 2x times x is 2x squared. Hey, look, they're still on the diagonal. 2x times negative 7 is negative 14x. Negative 8 times x is negative 8x. And negative 8 times negative 7 is a positive 56. So at the end of the day for this one, we will have x to the third. Combining these two, I will get negative 5x squared. Combining these two, I'll get negative 22x plus 56. So that's going to give me, again, a 4-term polynomial, but that's the final result that I get when I am done with the multiplication of those things. Now it talks about how is this process different from the process of multiplying two polynomials. The only thing that's different with this is that you must take two at a time and multiply the result times the third polynomial. Now, this is a fairly well written one of these. If this was going to be a constructing an arguments question, you'd have to write the things out here. I didn't actually say the lead-in sentence because I'm not as good at doing that as maybe perhaps some of my colleagues are, but this does give us a pretty good way of thinking about what we're going to do. And guys, I think that gives you enough information to know how you would do the work for section 1.5 in Algebra 2. So that being said, thank you very much for listening to me and for taking me through this lovely introduction to the Bechtel box, which you will see a whole lot this year. So thanks, guys.